welcome to the course on molecules in motion. We were discussing in the last class regarding the molecular motions in liquids, and in that doing so we had started on defining or finding out what are the strong electrolyte and what are the weak electrolytes. So, in the last class we had talked about how the strong electrolytes behave. We had discussed the Colorocious law in terms of how the molar specific molar conductance of a strong electrolyte is going to be linearly varying with the square root of the molar concentration. And we had also seen like how variation of the with variation of the concentration, how we can find out when we are approaching a very low values of concentration. If we can extrapolate the value, then we can get the value of the limiting molar specific molar conductance, and that was related to this expression, which was the Colorocious law, which we had discussed in the last class, that it is going to be always with increase in concentration, the molar conductivity or conductance is going to decrease for a strong electrolyte, and it is not that strongly dependent on the concentration variation, but it is going to give an expression like this, where if you plot a graph of lambda, that is molar conductance with under root of C, you will get a straight line approximation with a negative slope. That means, it is going to decrease, the molar conductance is going to decrease with increase in concentration. And how we are increasing the concentration? Concentration is increased and square root of molar concentration, whatever you have taken. So, from there you found out that the molar concentration is going to be directly proportional to the under root of C as the C approaches 0. And if as C approaches 0, what happens? This is approaching 0. So, the molar conductance is approaching the limiting value of the molar conductance, that is the naught, lambda naught. Okay. So, this is what we had talked about, characteristics of a strong electrolyte. We could not complete this. So, we are going to do that right now. So, what we did in the last class is only talked about Colorocious law. What we are going to do today is going to deal with another term, which is also given by Colorocious law. This is known as the independent law of independent migration of ions. Here ions move independently of one another in any very enough dilution or limiting dilution conditions. When C approaches 0, then the ions which you are having in the solution medium is going to be behaving like a like two independent ions. They will not depend on the other ion. So, you have the expressions contributions is the sum of the individual ions which you are dealing with. So, if you want to find out the limiting value of the molar conductance, what it will be? It will be nu plus into lambda. Lambda is the molar conductance of the positive charge, and minus is the molar conductance of the negative charge. So, these ions are moving independently of each other, and the conditions are very dilute. So, the limiting value of the molar conductance of the electrolyte can be found out when you add that conductivities molar conductivities of the individual ions, that is the positive ion and the negative ion, multiplied with the number of nu plus or minus, that is the number of cations or anions per formula unit. Like if you have HCl, the nu plus is 1, nu minus is 1. But if you have magnesium chloride, then nu plus is 1 and the Cl is going to be 2 Cl minus. So, nu minus is going to be 2. Okay. So, you see the molar conductances of certain values, limiting conditions are given at a given temperature. See how the values of H, Na, sodium ion, potassium ion and zinc ion are given here. You also see the anions associated with it. You see, we will be discussing this part later on. The limiting ionic conductance of H plus is pretty high, and then you have zinc ion also very high compared to these two, but this is exceptionally higher. Okay. So, limiting value of the positive charges which you are associating, you have these values, you add this up, and depending on what the new value is for the system, multiply that, and you should get the total value of the molar conductance for that particular electrolyte. So, Kohlrausch's law of independent migration of ions states that at infinite dilution, when the dissociation of the electrolyte is complete, then each ion makes a definite contribution towards the molar conductance of the electrolyte, irrespective of the nature of the ions which is associated. Okay. So, if molar conductance of ion is denoted by say lambda plus naught for infinite dilution for the cation, similarly for the anion, then according to the independent law of independent migration of ions, then the total molar conductance of the solute will be nothing but the summation of the contributions from the molar conductance of the anion as well as the cation. And these are the formula units, a number of cation per formula unit you are getting, and here is the number of in the anion you are getting per formula unit. Suppose you see this is an example given to you how to find out. Suppose you want to find out, these are all strong electrolyte system which we are looking into. You have sodium chloride, you have potassium nitrate, you have magnesium chloride, you have aluminum sulfate. All of these you see, how will you find out the molar conductance at infinite dilution? That will be the contribution of the cation and plus the anion multiplied by the number which is supposed to be associated with the number of cation or anion per formula unit. So, for sodium chloride it is going to be 1 so it is 1 sodium ion. These values you can get in handbook, this also you can get in handbook. So, if you can find out the value of the molar conductance at infinite dilution. Okay. Similarly, you see if you are taking magnesium chloride, then you have magnesium is going to be one magnesium ion. So, the plus charge will have nu plus is equal to 1 and nu minus is going to be 2. So, once you know the value of the anion specific conductance of the anion like chloride, then you have to multiply it by 2 depending on the type of electrolyte you have and how the ions are generated as per their dissociation in the solvent medium. So, this is what is the independent migration of ions, that you can sum up the molar conductance of the individual ions to get the total molar conductivity of the electrolyte. Now, let us move into the weak electrolyte system. Weak electrolytes are different, obviously are going to be different as we have discussed previously. The weak electrolyte dependence on molar concentration, the dependence of specific molar conductance dependence on the concentration is quite drastic. Before we go to that, we need to know what the weak electrolyte is, and I am sure all of you know that these are solutes which are not completely ionized in solution, and these are examples are Bronsted acid and bases like acetic acid, ammonia. The marked concentration dependence of the molar conductance arises from the if you have a say weak acid which is dissociating, if I take that as an example, the marked concentration dependence of the molar conductance arises from the displacement of the equilibrium constant towards the product at lower molar concentration. What does that mean? You have this, suppose you have this dissociation of, this is the acid which we have, this is, if this is the Bronsted acid which we are looking into, this is Bronsted acid, as you know, is going to be a proton donor. Bronsted base is one which is going to accept the proton. So, if this in aqueous medium, this is going to behave like a Bronsted acid, and the water liquid is going to behave like a Bronsted base. So, the equilibrium constant, if you want to look into, you can write down the equilibrium constant. It is going to be product concentration of the activity coefficient into activity concentration. That means, you should have activity of the product A and product B divided by the concentration of the reactant. Okay. Here water is a large system, so we is always in large excess. So, we do not take the concentration part into account when we are talking about the equilibrium constant. What is happening? We are saying that there is a concentration dependence of the molar conductivity arises because of the displacement of the equilibrium towards the product at lower molar concentration. So, if you have this as lower molar concentration, if this is going to be lower, then this is going to be higher. So, this is going to be dependent, that means the forward reaction is going to be accelerated. So, if you have a system where you have this is the equilibrium constant. For an acid, we also call this as a dissociation constant or acidity constant. So, this value is less than 1. What does that mean? If it is less than 1, means very small amount of deprotonation of water has taken place, and we classify them as a weak electrolyte. So, depending on the dissociation constant value or acidity constant value or the equilibrium constant which we are discussing here, we classify them as to how to what extent the deprotonation has happened for this particular acid. So, we are talking about a weak acid which is behaving like a weak electrolyte. Okay. So, what happens? The conductivity depends on the number of ions as well. Okay. So, one term which we just now discussed is the concentration, and another one is the number of ions. So, what is going to determine the number of ions? Since a weak electrolyte is not going to completely ionize in solution. So, the degree of ionization of the electron is important, that is alpha, and this, to what extent a particular solute is dissociated, is going to be determined by the degree of dissociation, and the higher the degree of dissociation, more is the number of ions generated, and hence increase in the conductivity value. And how is this degree of dissociation defined? Is the ratio of the amount of ions being formed in solution to that of the amount of electrolyte added to the solution. If it had been a strong electrolyte, then whatever amount you are adding, you will generate the same concentration of the ions in the solution. But when you are talking about a weak electrolyte, the number of ions generated on dissociation is not equal to the amount of the solute you have taken. So, suppose you have a weak electrolyte like acid HA. This is the reaction which we have. We have the hydronium ion plus A minus, which is generated, and we start with, we are trying to find out the equilibrium constant. We take the activity coefficients to be 1. Activity coefficient into concentration gives you the activity. So, instead of writing activity, we simplify by taking the activity coefficients to be 1 or ignoring it. So, what we have? We can take directly the molar concentration. So, initially it was suppose C in the beginning. What happens as the reaction proceeds? the amount which is dissociated is alpha. So, this will be alpha C, and this which is getting depleted is going to be 1 minus alpha into C. So, if you want to write down in terms of the equilibrium constant is what going to be what? Concentration of this into concentration of this divided by the concentration of this, right. So, if you are having this, you are having alpha square into C square divided by 1 minus alpha into C. So, if the concentrations are, since the concentrations are very low, what we can do, we can approximate to have k values to be represented as the ratio of alpha square by C into by 1 minus alpha, and alpha is the degree of dissociation which we have. From solving this, we can find out what the alpha value is. The degree of dissociation can be found out. This degree of dissociation alpha is called as the degree of deprotonation when we are talking about a weak acid. Okay. So, since the fraction of alpha it is only a fraction of so the electrolyte actually present as ion. So, to measure the conductivity at a given concentration, what you need to know is the alpha. So, the measured conductivity at a given concentration lambda, that is the molar conductance, will be nothing but alpha times the concentration at infinite dilution. Okay. So, indirectly what we are saying that it is a ratio, alpha is the ratio between what? It is the ratio between of what is the lambda value at a given concentration divided by what is the lambda value at infinite dilution, means when the concentration is approaching 0. Okay. So, this is another form which I have written. Why I have written the expression again is I hope to make you understand much more clearly. This is how what the dissociation was taking place. If it is fully if not fully ionized, then we wrote down what should be the if they are not fully dissociated, then to the fraction to which they are dissociated is if taken to be alpha, then alpha C is the concentration which is generated after when the products are generated is the hydronium ion plus A minus in aqueous medium. So, we can find out the value of K, and from this solving this the next slide has the solution for this. You get an expression something like this. This is known as the Oswald's dilution law for a weak electrolyte system. What you have rearranged the terms and you got 1 by lambda, that is the molar conductance for the weak electrolyte. If you plot that versus this one, C lambda, that means lambda at any concentration, 1 by lambda, that is one you are measuring that, you have conductometers, you can measure that. So, you measure what is the lambda at a given concentration, and if you plot that concentration into lambda in your x axis and in the y axis you have 1 by lambda, and then you take the intercept to conditions where C equal to 0, that will give you the value of 1 by alpha naught. So, 1 by alpha naught value can be calculated from the intercepts, because this is the intercept you have, right. So, this is the derivation which you have, how you are going to derive this. You just see, you have the equilibrium constant, how you have got the equilibrium constant. I hope you understand that. Then I rearrange. What I rearrange? I have alpha taken 1 to the denominator, and so I have this expression. So, I have 1 by alpha at one side and 1 by k, that is equilibrium constant, into this. Rearranging, see what it is just manipulation in terms of the rearrangement of the expression. You get this divided by alpha, you take it to this side, you get this, and AC divided by K. Again you rewrite 1 by alpha, break this up, this is going to be 1, this minus 1 goes to this side, plus 1, and this remains AC by K. Now substitute what is kappa, what is alpha. Alpha is nothing but the ratio of the molar conductance at any concentration C divided by the molar concentration at infinite dilution, and substitute that value here. Replace all the alpha values from this expression, then you get the ratio of this is lambda by lambda naught will come up, and then by lambda m at any concentration. And if you simplify this, this is the expression you are getting. This is nothing but the Kohlrausch's law, Oswald dilution law, which we had discussed previously. So, what we can have? We can have 1 by lambda plotted against concentration into lambda for a particular concentration system, and then we extrapolate and see the intercept. This intercept should be giving me the value of 1 by alpha naught. Okay. So, extrapolating to values C equal to 0 gives you the value of 1 by alpha 1 by lambda naught, that means at limiting condition of the molar conductance value. Now, you see how the variation is compared to the strong electrolyte. You will see at lower concentration it is having a moderately high value, and it drastically falls as you go at higher and higher value of the concentration. The variation of lambda is very large, and so it is so much to obtain cannot be obtained the molar conductivity at infinite dilution by extrapolation. In previous strong electrolytes, if you remember, we had plotted like this and extrapolated to get a value of the lambda naught, and this lambda naught extrapolation was done tending C to 0. But you see in this diagram, it is very difficult to extrapolate the value and get the lambda naught value from the plot of lambda versus C, because the graph is not going to be linear, the drop is very sharp. So, the variation of lambda with dilution can be explained on the basis of number of ions in solution. The number of ions furnished by the electrolyte in solution depends on the degree of dissociation, and the degree of dissociation is going to increase with dilution. The increase in dilution, the degree of dissociation increases and molar concentration increases. Okay? But you have to remember, when you are talking about a weak electrolyte, they are not completely dissociated. So, it is not possible for us to apply the law of independent migration of ions, Kohlrausch's law, to find out the lambda naught value of molar conductance at infinite dilution by extrapolation of this plot. Lambda versus under root C cannot be extrapolated to get you the limiting value of the molar conductance. So, Kohlrausch concluded the ions of all electrolytes begin to migrate independently as the solution is diluted. The ions in dilute solutions are so far apart, they do not interact in any way. Under these conditions, the lambda naught is the sum of the molar conductance of cations and anions, and at the infinite dilution. So, this is what we have for a strong electrolyte system, but it can be generally extrapolated. Now, what we have here, if I say that this is for the weak electrolyte, which is not completely dissociated, we can write this in the form of these expressions. According to the law, we can write down in the forms they should be dissociating H plus C3 the oxalate ion acetate ion. So, the acetate ion will have a lambda naught value, H plus will have a lambda naught value, but we cannot get this extrapolated to get the values, but we can say according to Kohlrausch's law we can divide them into 2 and find out the value of this independently, not from the graph of lambda versus under root of concentration for a weak electrolyte. Based on this, the known value of lambda naught, values of a cation and anion for a certain electrolyte, can be added or subtracted to get the limiting value of the molar conductance of the weak electrolyte. So, it may be noted that the lambda naught for a weak electrolyte can be obtained by an indirect method, and this indirect method is what was done by Kohlrausch's by repeated experiments using different types of electrolytes. I have given you this data. Observe the value of this is T lambda infinity. Infinity also means actually infinite dilution. So, it is sometimes written as infinity or it can be written as naught of different pairs of electrolyte with common ions, cations or common anions are almost the same. For example, the difference between the molar conductance of potassium and sodium is 23 irrespective of the anion. He did repeated the experiments and found out this is the difference. For nitrate, whether it is potassium or sodium nitrate, the difference in the cation and anion, the value of the molar conductivity is going to be 23.4. So, these are observations which he kept making and which is helpful to find out the molar conductivity of a weak electrolyte in infinite dilution. What he did, this is a classic example of how to find out the molar conductance of a acetic acid system, and you can solve various types of equations or various types of other weak electrolytes as you are doing here. According to Kohlrausch's law, I can divide them into completely dissociated ions, though we cannot do it extrapolated from the graphical method. We can theoretically imagine to be them to be completely dissociated. So, this is the infinite dilution of the acetic acid. What is the value of lambda? Equal to the lambda of at infinite dilution for the acetate ion plus the lambda value of H plus at infinite dilution. This equation can be obtained by the knowledge of molar conductance at infinite dilution for the strong electrolytes. Using a strong electrolyte, you can find out, for example, consider the electrolytes HCl, NaCl and sodium acetate. Now, sodium acetate is going to dissociate like this, acetate plus sodium ion. HCl is going to give you dissociate plus H plus into plus Cl minus. NaCl is going to dissociate Na plus Cl minus. So, I have to do this combination and find out if I can get the value of acetic acid. Like if I have to make it more clear, what I can do, I can have the lambda for the acetate plus H plus, that should be equal to lambda for the acetate plus the sodium ion. Okay. So, if you can rewrite this, that will be H plus into Cl minus and sodium chloride. In other words, I can write down the lambda of the acetic acid is nothing but the lambda naught value of the sodium acetate plus the sodium plus HCl minus NaCl. See, NaCl part is going to get cancelled off, okay. Sodium part is going to be also cancelled off, and only what you will be left with is the acetate and the H plus. So, that will be equivalent to something like this. So, that way you can find out the values of the infinite dilution values, molar conductivity values for a weak electrolyte. Thank you.